So we said that the distinguishing feature of Hilbert spaces over Banach spaces was the orthogonality of vectors. And in fact, so far we have seen one important result, that every closed subspace of a Hilbert space, due to the orthogonal decomposition M plus M perp, is complemented. So every closed subspace is complemented, unlike a Banach space where it may not happen. Okay, so now it is time for us to study this orthogonality in a little more detail, and so we come to the most important section in this chapter. So this is orthonormal sets. So let H be a Hilbert space. Let I be an indexing set. It could be empty, it could be finite, it could be countable, it could be uncountable. Okay, so let S be a collection of vectors ui, I in I, be a collection of vectors in H. Okay, so definition. We say that the set S is orthonormal if for every I in I, norm ui equal to 1. So that is the part, the normal part. Every vector is normalized, so every vector has unit vector, and whenever I is different from j, we have ui inner product uj equal to 0. So they are all orthogonal to each other, and they are all normalized vectors, namely they have norm equal to 1, and therefore such a set is called orthonormal. Okay, so remark, vectors in an orthonormal set, I will write ON for orthonormal. So orthonormal set are linearly independent. So if you have sigma alpha I ui, okay, so for some I equals 1 to n equal to 0, then you take any one uj, 1 less than equal to j less than equal to n. So you have 0 equals sigma I equals 1 to n alpha I ui comma uj. So if you take by linearity, this will be alpha I ui uj, and if I is not equal to j, it won't survive, and therefore this will be just alpha j norm uj square. That's the only term which will survive, which is alpha j. So each alpha j is 0, and therefore the vectors are linearly independent. Okay, so example again. So if you take Ln2 or L2, and then you take the family En. Okay, so if Ln2 say Ek, let us say, so let me write separately. This is the basis vectors, 1 in the kth place, 0 elsewhere, then Ek is an ON set. Similarly, if you took L2, the set of all Ek, so this is k equals 1 to n, here it is k equals 1 to infinity. These are all sequences, 1 in the kth place, 0 elsewhere, is an orthonormal set. Then let us take x equals 0, 1 with the Lebesgue measure. And then you look at L2 of 0, 1. Okay, so then if you wrote Fn of t equals root 2 sine n pi t. then easy to check that Fn n equals 1 to infinity is an orthonormal set. So integral sine square n pi t from 0 to 1 will be 1 by 2, and that will, therefore this will get cancelled, you will get 1. And if n is not equal to m, integral sine m pi t sine m pi t will be equal to 0, because that will be defined as a difference of some cosines, and then you integrate, you will get 0. Okay, so these are examples of orthonormal sets. Okay, so now we come to an important proposition. So this is called the Gram-Schmidt orthogonalization. Okay, so let H be a Hilbert space. Let x1 xn be a set of linearly independent vectors. Then there exists an orthonormal set E1 En in H such that for every 1 less than equal to I less than equal to n, Ei is a linear combination of x1 to xi. So it is, you take x1, then you get E1, you take x1 x2, you get E2, which is a linear combination of x1 and x2, and so on. So you build progressively this orthonormal set. So the span of E1, E2, En is the same as the span of x1, x2, xn, because each Ei is a linear combination of the x1, x2, xn's, and therefore they span the same space. It's orthonormal, so it's also linearly independent, and therefore you have any proof. Okay, proof. So x1, none of the vectors xi is not 0 for all I. Okay, so x1 is not 0. So you put E1 equals x1 by norm x1. So this is automatically a vector which is a unit vector. Okay, so now you take E2, so you consider x2 minus x2 E1 E1. Okay. Now this vector is orthogonal to E1, because if you take the inner product, you will get x2 E1 minus x2 E1 E1 E1. E1 E1 is 1, and therefore x2 E1 minus x2 E1 is 0. So this is orthogonal to E1, and it is not equal to 0 since x1 x2 are linearly independent, and this implies that E1 and x2 are also linearly independent, because E1 is just a multiple of x1. Okay, and here you have a non-zero coefficient for x2, so this cannot be the 0 vector. Therefore I can divide by its norm. So I define E2 equals x2 minus x2 E1 by norm of x2 minus x2 E1. So again E2 is therefore just a multiple of x2 for the first one. So E1 and E2 are orthogonal to each other, and E2 is a linear combination of x2 and E1, and that means it's a linear combination of x2 and x1. Okay, so now you proceed by induction. Okay, so you assume we have constructed Ei E1 EI minus 1. Okay, so for one less than or E1 to EK minus 1, for 1 less than equal to K less than equal to N minus 1. Okay, so EK for 1 less than EK, K less than this. So now we are going to define EK plus 1. So have been constructed. So you are going to define EK, So we now look at x k plus 1 minus sigma I equals 1 to k xk plus 1 ei. Okay. Now this again cannot be 0 because it's a linear combination of xk plus 1 and the e1 e2 ek, but e1 e2 ek by induction hypothesis are a linear combination of x1 x2 xk. So the whole thing is a linear combination of x1 to xk plus 1, and there is a coefficient 1 here which is not 0, so this is not equal to 0. So therefore I can now define ek plus 1 equals xk plus 1 minus sigma I equals 1 to k xk plus 1 ei divided by the norm of this, norm of xk plus 1 minus sigma I equals 1 to k xk plus 1 ei norm. So then norm of ek plus 1 equal to 1 and ek plus 1 ej is 0 for all 1 less than equal to j less than equal to k. Okay, so then induction hypothesis is complete, and therefore you can go on. So this can be done for any n, and you can construct the orthonormal base vectors. Okay, so now let us remark. Okay, so let us take Rn with norm 2, that is ln2. Okay, then you take x1 xn linearly independent vectors in Rn, and then we apply the Gram-Schmidt process to give you E1 En, which is orthonormal vectors. Okay, so now what? So we can, they span for any I x1 to xi and E1 to Ei. So for every I x1 to xi and E1 to Ei span the same subspace. So let us write xj as sigma I equals 1 to j Rij Ei. So now let A be the matrix whose columns are xj. Q be the matrix whose columns are ej, and R be the matrix Rij. So we have seen where you put Rij equal to 0 if I is bigger than j. Okay. Then A is invertible because the columns of the matrix are linearly independent. Now Q is a matrix whose columns are all orthogonal to each other, and therefore matrix Q is orthogonal. Q transpose equals Q transpose Q equals identity, because that's just the definition of an orthogonal matrix. So the columns of the orthogonal matrix are orthogonal vectors, and therefore we have shown, and this relationship is the same as A equals Q times R. So this is a theorem in matrix theory which we have proved. Every non-singular matrix can be written in the form QR, Q orthogonal, and R upper triangle. R is upper triangle. Namely, it's a matrix which will be, you have elements here, and below the diagonal everything is 0. Okay, so this is a theorem in matrix theory which we have now proved using the Gram-Schmidt orthogonalization process. Okay, so what is the use of these orthogonal matrices? They are very useful. Okay, so let us give an example. Okay, so you have a function. So example, suppose I have a function f which is continuous on 0, 1 to r. Then we want to approximate it by a polynomial. So you know various things. There are various Lagrange interpolation is one way. Another method is least squares approximation. What is the least squares approximation? You look for a polynomial p of t of degree, let's say, less than or equal to n, such that integral 0 to 1 ft minus pt square dt is equal to the minimum over all polynomials q in Pn, where integral 0 to 1 ft minus qt square dt. Okay, so what is this? Pn is this polynomials of degree less than or equal to n. So this is a subspace of continuous functions of degree of dimension n plus 1. Okay, so subspace, and we are going to look in the space L2 of 0, 1 because we are taking integrals here, and so L2 0, 1 is a Hilbert space. You have finite dimensional subspace, therefore it's a closed subspace. Then we know that you can always find a proximineal point. That means there exists a unique polynomial p which satisfies this condition, and that's called the least squares approximation of f. Okay, now how do we do this? So this polynomial p, what is it characterized by? So this characterization is pq is the same as fq for all q in Pn. So p is characterized by these equations, namely the inner product. We have seen this when proving the Lax-Milgram lemma, or even before that. Okay, so now since this is a linear space and this is a linear relationship in P and Q, therefore it is enough to check it, not necessary to check for all the elements Q, it is enough to check it only for a basis element. So basis of Pn, standard basis are the functions 1 p f naught, or rather the p naught, p1, pn, where p naught of t is identically 1 and Pi of t is t power I, 1 less than equal to I less than. So 1 t, t square, etc., that forms a basis. So if you take the polynomial P is equal to alpha naught plus alpha 1 t plus alpha n t power n. So this P of t, so P will be equal to sigma alpha I Pi I equals 0 to n. Okay. So then if you substitute that here in this equation, you will get following linear system. So you substitute here. So we are going to write sigma j equals 0 to n alpha j pj pi equal to fpi, 1 less than equal to I less than equal to n. So this gives you n linear equations in the n plus 1 linear equations, 0, sorry. N plus 1 linear equations in n plus 1 unknowns, alpha naught, alpha 1, alpha n. So once you find the alphas, you know P, and therefore you have found the P square. Now what is this thing? This can be written as AX equals capital F, where A is the matrix Aij. Aij is nothing but the inner product Pj Pi, and X is the vector which is alpha naught to alpha n, and F is the vector which is integral f p naught integral f p n. Okay, so then you have Ax equal to P if you solve this, and this matrix A, so Aij is equal to Pj Pi, and that is equal to integral 0 to 1 t of I plus j dt, which is 1 by I plus j plus 1. So this is a nice symmetric matrix with for 0 less than equal to ij less than equal to n. So this is n plus 1 by n plus 1 matrix, and therefore it is technically a nice, in fact it's positive definite also, you can check that because these are basis vectors. Okay, so it can be solved, but then when n is large, this is a very bad matrix. In fact, this is an example of a highly ill-conditioned matrix. So this matrix whose entries are 1 by I plus j plus 1 is an example of a highly inconditioned matrix. This is a terminology in numerical analysis, which means small errors in data lead to large errors in the solution. That means round off errors which are small, which are natural to occur, will blow up when you come to, so the solution which you get by inverting this matrix will be nowhere near the real solution, because there will be, computer will make a lot of errors, and these, a matrix of this nature will completely destroy it. So it is at this situation that the orthonormal basis, so suppose we do the Gram-Schmidt orthogonalization, and then we get Q0, Q1, Qn is an orthonormal set got from P0 Pn by Gram-Schmidt. Okay, so we get the Gram-Schmidt process, and then so let me write Gram-Schmidt. So then we want P can now be written as sigma alpha j qj, j equals 1 to n, and then it's very easy now. If I take P inner product qi, this will be sigma j equals 1 to n alpha j qj qi which is just alpha I, because only one of the terms is going to survive, all the others will disappear because of the orthogonality conditions. Therefore, there is no need to solve anything. I therefore can write immediately, I know what is, so I can write P is equal to sigma j equals 1 to n of P qj. That's all. So I have got the polynomial without any difficulty. Okay, so this is the one of the uses of the Gram-Schmidt orthogonalization. It helps you to immediately write down the solution. So now let us look at an example of this Gram-Schmidt process. So let us take the space L2 of minus 1 1, and let us take Pi of t is equal to t power I equals 0, 1, 2, etc. Okay. So we want to construct the Q's. Okay. So let us take, so what is P naught? So we have to take the L2 norm of P naught. So that's equal to integral minus 1 to 1. P naught is constant, so this is just dt, and then you have to take a power half, and that is of course root. So we write Q naught of t is equal to 1 over root for all t in minus 1. So now we have to look at the function. So now consider the following function, t minus, so this is the first P1 is t, okay. So t minus, I am going to take the inner product of t with Q naught. Q naught is 1 by root 2, so 1 by root 2 integral t dt minus 1 to 1. Okay, so that is just the inner product of Q, and then multiplied by Q naught. So I have to write Q naught of t, which is 1 by root 2. Now integral of t is odd function, so if you integrate, you have got t square, which will plus 1 and minus 1, it's the same, so we will get 0, so this term will not come, so this is just t. And then it's L2 norm of this, so call this Q1 of t. So norm of Q1 of t in L2 is nothing but, if you do the calculation, this will be root 2 by root 3. So what is this? This is, you have to take integral t square from minus 1 to plus 1 and then take power half. Okay, so that will be root 2 by root 3, and therefore you write Q1 of t is equal to root 3 by root 2 times t. Okay, so I have to divide by this. Now this is for all t in minus 1 1. Okay, so now let us take Q2 of t. So this will be t square minus t square into p naught. So that will be 1 by root 2 integral minus 1 to plus 1 t square dt into 1 by root 2. That will be first one, and then you have minus you have to take the inner product of t square with this function q1, so that will be root 3 by root 2 integral minus 1 to plus 1. So t square with t will give you t cubed dt, and then you have to multiply by root 3 by root 2 into t. So if you simplify this, again this t cubed will not give you anything, this integral will not give you anything, because you are going to just get 0, because you will get t power 4 when you integrate. It's an odd function, and therefore you will get 0. So if you simplify this, you get t square minus 1 by 3, and then if you compute its L2 norm, so norm Q2 in L2, so this is a computation which you will have to do. So that will be 2 root 2 by 3 root 5. Okay. So then you have to write Q2 of t equal to root 5 by 2 root 2 into 3t square minus 1. And similarly you can proceed like this, and you can show, for instance, that q3 of t will be equal to root 7 by 2 root 2 of 5t cubed minus 3t. So here you notice something. The even polynomials which you get are only involving the even powers of t, and the odd polynomials are involving only the odd powers of t. That is just because of the space minus 1 1 and the inner product which we are here. Now remark, if you have q tilde nt is root of 2 by 2n plus 1 qn of t, these are nothing but the famous Legendre polynomials. So the Legendre polynomials in applied mathematics, very famous in numerical analysis also. So these are orthogonal polynomials. They also come from differential equations you might have studied, and these are nothing but you take 1t, t square, etc., apply the Gram-Schmidt orthogonalization in L2 minus 1 1, and then you get them with the scaling factor in the front. Okay, so that is the example of this. So now we will have to look, we want to study in detail the properties of orthonormal sets. So we have seen examples of orthonormal sets, we have seen examples of the Gram-Schmidt orthogonalization process, we have also seen an application of why such orthogonalization is desirable, and now we will now study the important properties of this.